Good morning, everybody. Indeed, I'm going to talk about BMI. The contents is just recap what was BMI, what did it stand for, extensions, what changes being discussed. It is being discussed, some are being developed, but then delta, what do we do with BMI at delta is demand for parallel coupling and for parallel applications. So BMI is the basic model in place, started about 2007. Primary developments happened at the University of Colorado Community Surface Dynamics modeling system group. Current version is 2.0. It's a framework session, but BMI is a primary focus is the interface. It's on standardizing the interface for the model. Then you can link it up using your own framework or an example framework developed by either the University of Colorado or other groups. So PMT, second generation of model coupler from University of Colorado Python based. And the main design principle is that BMI component does not make any calls to the outside world. So it's the outside world that calls the component, but not the other way around. Since there is no infrastructure, it's always directed from the outside to the inside. It's so-called, call us, we'll call you. So there are, the model exposes various functions. You have version 1.1 that is now on the drive. You'll see a list of the functions support. Basically, it includes the times the general initialize, time step finalize, and functions to describe metadata, to describe the component name, what are the input quantities that it can accept, what are the output quantities that it can provide, what flashes are they defined, functions to retrieve them, and for those reasons, can you give me a pointer to data? A little bit more tricky, but and then the metadata about units, things like that, start time, end time, time step. The details can be. For a long time, BMI was kind of determined by the University of Colorado development staff, of course, in informal collaboration with other groups. There is, since last year, there's a BMI council, like a board or steering group, at least discussing things. Notice that there are contributions of different kinds of lab on some more managerial, more technical, so the discussions go all kinds of directions, but besides the University of Colorado, there's now involvements of NOAA, National Weather Service, Center, USGS. I'm there for the half of Deltaris. Representing Deltaris, there's the National Dutch E-Science Center and the Delft University, related to the e-water cycle project that was presented at the online version of this previous coupling workshop online. Okay. So, what is the ongoing discussions? One is that people started asking about data assimilation, things like that, or storing states, restarting. And so we said, well, what are quantities that the system should store and reload? Do you say have the model have a state dump option, or can I query the state vectors, quantities, and give back? If you look at the goals described in the API, we currently have a get input variables and a get output variables. One of the discussions, we have a get state variables, or should we just go back to having get variables and then have per variable a list and a kind of property? Is it input? Is it output? Is it state? Or you could think of other quantity options to be added in the future. But that's the first one. Then there was for coupling with ModFlow, with USDS, an extended model interface defined, which allows for coupling at iteration level. So BMI supports coupling at time step level, and with this one had to go towards iteration level for some application. So that's where the idea of an extended BMI was introduced. Triggering the next point, should we have a BMI core that you can implement and then have BMI extensions that not everybody needs to implement? Can you then query your model whether it implements that feature? So you should note that most of the BMI components are shared libraries. DLLs on Windows shares libraries in the general context, and so they are only brought together at runtime by the end user. So that's where the framework then needs to query, okay, what do I have? Or you can also hard code a framework or a self. Then there are discussions about language bindings. Currently, Fortran, C, C++, Java, and Python are included, but for some applications, there's need for and there's a growing demand for Julia. So that's where discussion is going, to which degree is it community effort and to which degree central coordinate effort. Coordinate reference systems. Most of the models discussed here are in global coordinates, but going to smaller scales, we are also engineering models which are local coordinate systems. So all the coordinates transformation issues come in. We have not actually discussed the Council, but the parallel interface is on the list of topics to be discussed. And so I hope to get feedback there. BMI at Deltaris. We have several models now fully or partially BMI compliant. The most dominant is the Delft3 flexible mesh suite, various components. So the flow kernel is an unstructured flow solver which can be used at global scale, but also at a local urban scale. So you can go from ocean models to sewer networks. So that's 1D, 2D, 3D integrated. Therein is also sediment transport, morphology, bed level changes. That's fully integrated. It's not a separate component. D waves can have multiple nested grids using Swan from Delft University. Then we have the water quality component. It's similar to the biogeochemistry modules mentioned yesterday by now I am forgetting it. So the real-time control for human control of barriers. So you have structures in your rivers which you can open and close based on certain rules, which is more like a scalar operations, which are irritatingly difficult for parallelization and scalability. And there is a dimmer, which is kind of our Deltares version of the framework with which we couple the components that BMI to the various components. And there is a hydrological model, which is programmed in Julia, the latest version, which is based on Cartesian meshes. We work a lot together with the USGS on mod flow, groundwater, smaller scale, X-Beach that also has a lot of processes, but sometimes even coupled. And then the swings, which you use, and so a lot of the issues being discussed, we pop up somewhere in the Deltares development. So it's a combination of all kinds of elements that we want to couple. And then, end of last year, I looked at the different applications and noticed that a lot of the groups want to start using scale to bigger machines, not just run on a single node. So we have the flow morphology waves for coastal development that want to run in parallel. The surface water and groundwater models they want to scale. We have X-Beach more, wind-driven sediment transport, vegetation, and groundwater. They want to do that basic, just flexible mesh with vegetation for long century to millennia timescale morphological development of deltas. Joshua Online triggered a question with dflow FM with PALM for urban thermodynamics, see if we can couple it where PALM is already running up to 1,000 processes. Can we then link it up with a model for the water bodies? We have a similar wind farms with another, not yet complete, but discussions are going on. And then Noah asked, well, can you export all the quantities and make them available through the BMI for integration in their hydro fabric for the next generation system, which also requires redirecting diagnostics through a different interface, but also different type of variation. So this needs to have a consistent approach rather than everybody inventing their own extension to BMI. So what are we going to do? Just simple block diagram. We have the kernel. We implement BMI as the basic interface, and then you can wrap it and couple it using one of the technologies in the frameworks discussed over here. iOS or whatever may follow if this doesn't happen, or we have PALM as its own coupler, so maybe that one will be used. So we want to abstract our kernel from what happens in the outside world. But to do that, we first need to make sure that we have a BMI interface that is defined for how it should react for a parallel environment. So this is to the point where I'm that I have reached now. We are looking at the various interfaces discussed here and also outside, and it's precise that we are also now looking, it's more popular for multi-physics kind of application, but it looks in the end very similar. So you need to pass the MPI communicator to your component, and that's where already discussion starts. If we do that as part of the initialize call, then the basic interface is no longer the basic interface, because it's now defined without an MPI communicator. So even if we want to, we cannot see this as an extension anymore. So can we see parallel support as an extension to the standard, or should it be an integral part of the standard? That's the discussion, because if we change the initialize call, then everybody, even if they are not implementing a parallel component, have to accept an MPI communicator. Or should we, and that's the way we handle it now within the Delft3D system, we initialize it, we do a BMI set variable call on the on a known name for the MPI communicator, but that brings the system in a little bit of a fuzzy state because BMI component is not initialized otherwise, but yeah, at least then during the initialize call you can start doing your initialization in the parallel line. Then I think the querying of meshes is the standard bit is where you have a full 2D 3D mesh. It's well identified by the various systems, but we also have barriers, weirs, and all kinds of other locations where we do special things, which is not typically captured by a mesh. And so how do you discuss that, or how do you proceed with that? In the current version of Delft3D, we return for the meshes partition data, but for the hydraulic structures and things, we have merged it onto the master node because then we have a consistent set there, but that's maybe not what we want for the future if you start thinking about it. And also we may have drifters and drogues in the system which then start shifting between partitions. So a lot of challenges that we can think of. Then the component querying, once we know what is where and how long the arrays are, I think querying it is already covered by the standard existing interface. And, well, this is which quantities there are, and getting and setting the data should also be fairly straightforward. I think that, yeah, that was already my last slide. I'm looking for feedback, suggestions, discussion on these topics where we are about in the next couple of months need to define the extended BMI interface. This is the best meeting I can think of having such a discussion. If it had been at the end of the year, you would have heard my detailed proposal or our detailed proposal, but now it's more of an input collection.
Okay, thank you. Okay, hello everyone. Good morning. I'm sorry that I cannot join the workshop in person, so I have to give the presentation about our latest version, coupler C-3 online. Thanks Arnold for such an important opportunity. So C-3 is an integrated coupler infrastructure for Earth system modeling. So next, I will briefly introduce the background. The first question coming to us is why we should develop a new coupler version or family in China. Because there was no coupler team in China before 2010, while there are a lot of coupler models developed in China. Coupler teams outside of China are generally inconvenient to directly serve Chinese models, and we know that there are a lot of new requirements regarding couplers from Chinese model development. So C coupler should be able to serve various model developed in China, especially address the new requirements. It is true that China does not pay enough attention or supports for the software development for models. I think most of the efforts are paid for the scientific part. So this slide shows the milestones of our C coupler development. We finished the first version C coupler 1 in 2014, the second version C coupler 2 in 2018, and we finished the third version C coupler 3. It is also the latest version in the last year. This slide shows the general architecture of the coupler models with C coupler. It has two key ideas. First, C coupler can serve various coupling configurations in different coupler models, and a component model can have an identical code version in different coupling configurations. Motivated by this general architecture, we designed the general software structure of C coupler. It consists of a configuration system, a coupling generator, and a runtime software system with various functionalities and frameworks. This architecture, this software structure is like to the computer system with a computing language and the compiler and the processor. So we try to make C coupler as flexible as possible. Guided by the general architecture and the general software structure, we finished the first version, C coupler 1, with some functionalities such as the static 3D coupling capability. I think the most important contribution of C coupler 1 is that it proves the feasibility of the new architecture and the overall design of C coupler. C coupler 2 has some new features based on C coupler 1. For example, the flexible and automatic coupling generation, the dynamic 3D coupling capabilities that can handle the coupling between the 3D grids with variable vertical coordinate values, and it can conveniently achieve incremental coupling and model listing. More details about C coupler 2 can be found from the GMD papers published in 2018. With these new features of C coupler 2, it has been used in real models in China for a number of Chinese institutions and several key research projects of China. So when we think about the development of C coupler 3, we are involved in a key research project in China, which enables us to take a look at various kinds of software structures for supporting the model development, such as besides the coupler that is important for achieving model coupling. We find that there are other kinds of software infrastructures, such as the data assimilation frameworks for conveniently developing the data assimilation system, and some tools or libraries for model parallelization to conveniently achieve efficient parallelization of component models, and also the integration framework for conveniently integrating physics parameterization schemes into a physics package, and also the frameworks for conveniently and efficiently data input and output. And there are simulation platforms that are known as the scripts for configuring, compiling, and running the model simulations. And there are also tools for software testing to improve the reliability of model codes and software. But for most parts of most kinds of the software infrastructure, there are no software products developed in China. So we try to achieve these software infrastructures in the same platform based on C-2. So we make C-3 as an integrated software coupler platform with various frameworks. C-3 now becomes a scalable coupler for ultra-high model resolution. And it has a common coupled ensemble data assimilation framework. And it has a common Hello Exchange library for model parallelization and a common module integration framework that can integrate 3D parameterization schemes into a 1D, just single column physical package. And it also has a common I/O framework to improve the I/O performance and make the data input, field input output as flexible as possible. So next, I'd like to briefly introduce each new feature of C-3. First, I will introduce the new parameterization schemes, the new parallel optimization technologies to make C-coupler capable for ultra-high model coupling. We looked that C-coupler 2 has some disadvantages, especially for its high initialization cost and big memory usage, even when the model resolution is low. So we finished a series of technologies for faster initialization and lower memory usage, including a distributed parallel triangulation algorithm. The triangulation is used in C-coupler series for generating the remapping weights. And we also developed a distributed routing network generation implementation in C-coupler 3 to improve the performance, the initialization of data transfer based on the M multiple N communication. And we developed a distributed management of horizontal grids, also with the distributed generation of remapping weights to lower the memory usage, especially for the ultra-high resolution model coupling. And we achieve the parallel I/O for remapping weight files. Such kind of each optimization technology does not change the bitwise identical results based on C-coupler 2. So I'd like to introduce that C-coupler 3 is fully compatible of C-coupler 2. All existing APIs of C-coupler 2 can also work in C-coupler 3, and C-coupler 3 can achieve bitwise identical results with C-coupler 2 when using offline remapping weight files. This slide shows the performance of utilization of C-coupler 3. So we can see the last part, the last row here. The resolution is very high, just about 1.5 kilometers globally. And the number of processes, I think, is big now without OpenMP threads. So this column shows the time of coupling initialization with C-coupler 3. The initialization time is less than 1 minute. And the C-coupler 3 can generate large size remapping files for these test cases with, I think, the time for remapping generation in parallel is acceptable currently. And the memory usage now is controllable, I think. So it can work for most cases now, C-coupler 3. But the older version, C-coupler 2, cannot handle such high resolution. Next, I would like to briefly introduce the common Hello Exchange library. Hello Exchange is a fundamental task for model parallelization. There are a series of operations in Hello Exchange, such as data packing, MPI communications, and data unpacking. So we developed a common header exchange library based on C#2. It can support any kind of grid structures, such as structured grids or unstructured grids, and can support any kind of parallel decompositions, header regions, and any dimension order of fields. And it can automatically finish all operations for header exchange via simple APIs. And it supports the parallel communication based on data transfer functionality of the coupler, and supports the asynchronous communication and can exchange multiple fields at the same time. So the implementation of this library is simple in C-coupler because of the architecture and the foundation of C-2. So we just provide several new APIs for the header exchange because C-2 has supports a series of APIs that can be used for header exchange. This slide shows the performance of the header exchange library. We just use this result to prove that the benefits of exchanging multiple fields at the same time to improve the performance of MPI transfer, as it enlarges the MPI message size for better MPI bandwidth. I'm sorry that I will not introduce the common module integration framework with details. More details can be found from our C#3 manuscript that is under review by the GMD journal currently. But this module integration framework will be briefly introduced in the part of the DA framework. So next I will introduce the common I/O framework. We try to use this framework to improve the I/O performance of C-coupler, and also hope it can be used to help the model, the component models to achieve parallel I/O and for flexibly inputting and outputting the model fields. So it supports parallel I/O currently using the PLSDF. And it can automatically input model fields from a time series dataset under specified time remapping rules. And it can also automatically conduct time interpolation when necessary. And it can automatically output fields almost under any time series specified by the configuration files in XML format, and it can automatically conduct data interpolation between different model grid and the file grid when inputting or outputting model fields. So more details about this framework can be found from the GMD submissions. Currently is under review. So this slide shows the APIs for the I/O framework, and benefiting from the existing APIs and the functionalities of C#2, we just developed several new APIs, and the code for this I/O framework is about, I think, maybe less than 6,000 lines of C++ code. This slide shows the performance of the I/O framework. The left two figures show the performance when inputting or outputting a 3D field with large size. And the left two figures show the performance of when inputting or outputting a 2D field, whose size is much smaller. So we can find that the parallel I/O can accelerate the performance of inputting or outputting a 3D field with large size. That is reasonable, I think. So as the last part, I will briefly introduce.
Lee, you have still 2 minutes to go.
Okay. So the common coupled ensemble data simulation. So I will just, because of time limitation, I will neglect this part. So this framework enables to conveniently integrate a DMSR into a model as a procedure that can be directly called by the model ensemble based on the DLL technology. And this framework can automatically and efficiently handle data exchanges between the model ensemble members and the DMSR without global communications. These two features are essentially achieved by the common module integration framework. And it enables to conveniently specify statistical processing among ensemble members for the configurations. So we develop an example weakly coupled ensemble data assimilation system based on this new framework. This is a code change. We just keep the model code and the DMSR code unchangeable and developed the extended interfaces and also the XML configuration. We evaluate this performance with the Wolf model and design 4 sets of experiments under different resolution, different numbers of ensemble members, and different numbers of processors. So the experimental results on each set demonstrate that this framework can improve the performance, just reducing the execution time of the DA system, the original offline DA system. So, for a brief summary, C-coupler3 is a common coupler platform with fast initialization and various frameworks, and C-coupler3 can be fully compatible to C-coupler2. Thanks a lot.
So this presentation will be about concept and the tool that helped us to solve one specific step in the model simulation workflow. Thank you. And the concept and the tool were developed at SMHI, but we had some really important help of Eric here from Fairfax, who in the context of OASIS dedicated user support funded by ECNES came to SMHI and helped us specifically with the parallelization, as we will see later on, which I knew in theory it would work, but then of course there's always problems in the practice, and Eric managed nicely to solve this. And then also we had a lot of discussion and with and Eric, and he explained a lot about the regrading methods to us, so we could better understand what we were actually doing when we're coupling. And this will be OASIS. The concept might be somewhat general, but the implementation certainly is focused on OASIS. So if you're using another coupler, sorry. That works. Okay, so let's dive in right away into how a coupled model is set up with OASIS in terms of coupling configuration, right? At the center of this sketch, you have the numcouple file, which is the main name list if you're a Fortran programmer, config file if you use any other language, which has a lot of information about the coupled system, such as listed here. But there are other files around. There's a bunch of netcdf files that describe the grids, the coordinates of the cells and the corners of the cells, the areas, the mass, and so on. Then there are the remapping weight files, also netcdf, which we have discussed in this workshop quite a lot for different reasons. And OASIS uses them, of course, to actually remap the grids. And then last but not least, you have also the model code where you have the OASIS calls, which both make the link between the model component data structures, the arrays, and the OASIS coupling fields, but also determine the sequence of coupling by calling OASIS put and get. And then you have these arrows here, and this is my sketch, and one interpretation of the arrows is like required consistency, right? So if you do a change in the numcouple file and change a grid name there, then this has to be reflected in the grid description files, of course, because the netcdf variables, they have to match. And if you change, for example, in a numcouple, a regridding method because you want to try something else, then that has to be matched by the remapping weight files, of course. And the same goes for the things you have in the code. So the issue, and that has been an interesting discussion in I think the first evening in the Surfex there. For us, there are many reasons or frequent reasons to do actually changes in an uncoupled file, be it in model development, both when you prepare for the next CMIP model version, but even more in the climate research sense. So some PhD student want to change something. So they go in an uncoupled file and do changes, and that has an effect. But even if you have a released version, ECRS is quite a diverse model and it has a diverse consortium, so there are all kinds of different configurations, and if you switch on or off your biogeochemistry in the ocean, that has an effect on the numcoupled file, and as the arrows indicate, that has an effect on other files. So this is a problem for us. You can solve that, and in fact many groups do, by providing all the possible grid files, all the possible remapping files, but of course this has a combinatorial complexity, right? If you look at the combinations of things. So let's look a bit even closer at the non-coupled file. As we said, there's a lot of information in it about the coupled aspects of your model. And to be honest, we always had an issue or certain issues with a non-coupled file, and that's not the first time we discussed this in this workshop series. So if you look at the information stored in there, it's partly repeated. Just by example, you give the list of fields, but then you also have the number of fields, which if you count the list, that's doubled information. And it's a picky example, but you get the point, I hope. The information is at different scopes. You have some information that goes for the whole system, some is going for components, which is not as such a problem, but it's also not in its format. It's not completely hierarchical. So, I mean, you can order the fields that you are changing in any way you want. You don't have to group them by components or by, and then talking about the format, it's non-standard, it's a column-based syntax, and probably most important of all, there's one parser. That's the one that's built into Oasis, which means you can't use the parser easily, right? Oasis parses the file, but if you want to parse it, you have to write your own parser. Copy it, but yeah. But as we know, I mean, the information in the file is needed or originates in other parts of your workflow. If you have a coupled model with Oasis, then you need to start your executables. That's information that's also in the numcoupled file. So there are two alternatives. We could have a different format or change the content of the numcoupled file. And we've discussed that a long time ago, and simply there's no real interest in the community to do that. So given up a long time ago on this.
To change the format.
To change the format, yeah. Okay. To convince you to have another format. The other option is just not see the numcoupled file as such in that format as the origin of information. Just store your information somewhere else and generate the numcoupled file. And I think many groups are doing that. We were doing that in our old model version by a rather crude templating bash script thing, which in the end meant we would store the coupling information in a bunch of environment variables, which is not really helping in the long run. So, but still the auto generation idea is what we in the end do. But it's not really, at least not only about the format. It's really about that the information is needed elsewhere, and it's needed in a form that makes it easy to process and do stuff with it. So what we really want to do is to have this information available, to be able to build small tools that help us in the workflow, setting up the model and running the model. All right, so once or recognizing that we want to have the information available, what is it that is stored in the NumCouple file? So what can we have a good data model for that? So this, and now we're going into more of the implementation questions. So what we did is setting up Python, using Python data classes, but it's not even important that that's a certain Python feature. Just think of an object-oriented representation of the NumCouple file. To do that, we invented the concepts of links, which basically say is a combination of a source and the target and the regridding method. And those have endpoints, and we'll see that on the next slide. But basically, we invented or recognized the objects that are hidden in the NumCouple information. I will mention the grids later on. The one thing that is really nice, once you have an object, I mean, at least in Python, it's very easy. You can make the object printable. So we have an object, and when you say print NumCouple, it will write the NumCouple syntax on your screen or in a file. You can implement that. You can build in the NumCouple syntax into the code. And you have an object and you can print it. You can modify it and then can print it. So this is roughly how it looks like. I mean, this is not rocket science. If you read it, you will recognize most of the things that you need to write in the NumCouple file. Just there's a hierarchy now. So NumCouple consists of a couple of global attributes like the runtime and the nlock PRT. We didn't even bother to rename it for the time being. And then it consists of links, which have the link endpoints, and then there's the transformations, which you will also recognize from the NumCouple syntax. And then the link endpoints, they refer to grids. And the one thing that's important here, or that I would like to mention, is that grids in this context, I mean, the NumCouple file doesn't really know much about the grids. It's basically a name. It's a four-letter name. So the actual grid information that is needed to write the grid files is handled elsewhere. We have what we call base grids, which is another base class, and the base grids, they are a base class for actual specific grids like the Orca grid, IFS grids, regular grids, and so on. Just to say that as far as the NumCouple knows, there's just a grid, which is has very little information but links to the actual base grids. All right. So with that's the concept or the framework part of the whole thing, right? Basically, all we have is an object, is a class, NumCouple. You can instantiate it, and the nice thing is you can instantiate it from YAML, from whatever. It's very easy to write a parser. In Python, that's 3 lines or so, and you can decide if you want to have a YAML representation, JSON, or whatever. That's not something that you can execute yet. It's just the data. You have it there, it's object-oriented, and you can you can do, you can code things with it. So I have two use cases where we use it. One, and that goes back to the actual title of the talk, and to the workflow issue that we have. The problem is, as we say, as we said in the beginning, that everything is interlinked. If you change the num couple, you will need to change the grids.nc and the remapping files. And as explained, this is prone to errors if you don't have a very complex framework around it. So we would like to compute on the fly most of the things. And Oasis actually has functionality to write the grid files. And we want to plug into Oasis and trigger to write the grids and the areas and the mass.nc files. So we don't implement that on our own. And okay, maybe I didn't mention that explicitly, but all this is PyOasis. And so that's really the game changer for this kind of tools. We are able to go into Oasis and ask Oasis, please write the files, and here's a nice object-oriented representation of the grid, and use it to write the grids and C file. As far as the remapping weights are concerned, we all know, I mean, you just don't provide them, and Oasis will compute them for you by script at the beginning of the run. But that doesn't work very well because it's not. It takes a lot of time, and also resources, mostly because what you do when you start the model, you're not concerned about the grid, the weight generation process, and your number of nodes and OpenMP threads is not really optimized for the weight generation. It's optimized for your model run, which means I'm not sure how far I should go into the detail, but Oasis produces the weights for each source target remapping methods combination always on the source, which means if you have a source in your source component that has multiple links, then those weights will be computed sequentially. So we would like to improve on that. So what we do, we read the num couple information. In our case, we use a YAML file. And then by using PyOasis, we automatically create, set up, run a fake model. So it's a model that has one component for each of those links, making sure that each component only needs to compute one set of weights. For that, the num couple, since we have this nice object, it has an option to reduce itself to throw away all links that would result in the same set of weight files. But it has only the links that are distinct. And then we use Oasis to first create the grid files, grids and areas and mass. And then we run this fake model until Oasis end def, which will create the weight files, and then we shut down the model and we're done. So the last thing we do then is to create the real num couple, because you remember we wanted to auto-create the num couple file. So not the reduced version, but the real version for the model. So after you run this, you have the grids and the grid file, grids, mass, areas. You have the weight files, and you have the num couple. Okay, and you do that in a little pre-processing step, and you assign the resources that are needed for the weight calculation, not for your model.
And it's in Python.
And it's in Python. Okay, here are a lot of more implementation details. Just let me see what I would like to mention. I said most of it already. Yeah, there's one thing that is interesting to mention. To make this really work, and Eric, again, helped us with that, there's one little barrier in the Oasis code that will destroy your MPI parallelization over the weights. And so this was removed. then parallelization works.
Parallelization of the,
At the MPI level, one.
you can generate more than one file at the same time. Regridding file at the same time.
Yeah, basically all. I mean, you had as many MPI processes as you have wait files, but they would still wait for each other.
Okay.
So if you remove that barrier, they all go at the same time. All right, and again.
I think you are.
3 minutes. Okay, so basically, and I intentionally did, I mean, this is a qualitative, mostly qualitative evaluation of the performance. Basically, it does what it should. The original implementation in ECRs had a lot of this sequential weight creation. If you use one MPI process per weight file, you already get a big advantage, parallelization. And then if you switch on OpenMP, basically weight generation for everything except high or extremely high resolution cases will be so quick that you don't bother. All right, and very quickly, a second use case, and again, that's all based on the data model of the num-coupled file. Once you have this, then create nice tools. So we wanted to check interpolation methods, and there are these OASIS examples in the OASIS source code. When you download it, this is interpolation test, but they have predefined grids, and what we want is really to use these interpolation tests with our grids, our model grids, the grids we use in the model, and with the methods we use in the model as well. So, and since we have the num-couple information nicely in the YAML file that's used for our model run, we can use that information to make the actual interpolation test. So what we did, we re-implemented the test functions from the benchmark article, which is usually 1 or 2 lines of code in Python. Then again, we set up automatically this fake model, this time not only for generating the weights, but to sending a test field from a source to a target. And then we can, as in the article, we can evaluate the error. So, and basically what it does, it gives you numbers on the terminal for the errors, but it will also plot. And these are examples. And again, the thing is that you just change your num-couple information and use the exact grids and methods that you want to use in the model. It's not a separate test framework. It uses the actual num-couple information that you would use for the model. And you will get the results for the setup that you are really using. All right, with this, I'm finished.
Okay,
Thank you.
Hello, everybody. So I'd like you to introduce the XOS team that is, everybody is here, that for development, there is me, Yann here, and Arnold, for testing and integrating CIS into IPSL model. He's also the Mr. Coupling for the IPSL ESM. So for introducing new feature, what? Okay. Yes. Just make some history about a major version of XIOS. So XIOS is about 10 years ago old, and so the first release, XIOS 1, was developed and targeted for I/O output with 2 main ideas. That means the first one was to outsource the I/O description outside the model in external XML file using a very compact and flexible description with a hierarchical concept. And in the model, we keep a very simple interface, send the variable of the field to the XIOS server. That means XIOS send field interface with just the ID the ID, this is the string, character string, and the address of the field. The second idea is to use the asynchronous parallel I/O servers to make the writing and to be able to overlap the transfer and the writing time by computation. And so the server use a parallel file system capability through NetCD4 parallel. And so this first version of XIS1 was targeted for a full ESM model and was fully interfaced with the OSs. For the XIS2 release, we had the asynchronous reading from servers with a similar interface than for writing field, XIS receive field with the same minimalist interface. And more important, we have the capability to make parallel computing in terms of workflow on the client part. So what can be achieved in this workflow? We can achieve time integration, like averaging, etc., minimum, maximum, accumulate. We can make a combination of fields to create new fields that can be sent after the servers. And we can also apply a spatial transformation. That means we change the geometrical shape of the fields that are sent to the workflow. So, for example, you can implement horizontal and vertical interpolation, subdomain extraction, reduction, allow extension, allow exchange, etc., etc. So, in the coding workshop, now it is important to make a focus on the interpolation. So, XIS have a very precise and efficient interpolation method that are done on the fly, and the weight computation at the initialization can be also done in the fly very quickly. So, with this system of filters that can be chained, you can achieve a very complex workflow before the data are sent to the server, or symmetrically, data can be received from servers and also enter to a system of filter and be returned to the model. You cannot also that you cannot, it's not mandatory to use the server. You can enter to the workflow, make specific operation on the field, and it can be returned to the model. Here. For the 2.5 version, we add a second level of servers. So you can see on the right, not very well. Possible to minimize. Yeah. Yes, that means the first level of server will aggregate the data of many clients and is able to redistribute this data to a second level of server. And so each pool of this second level of server have some dedicated files, and you can achieve more concurrency by writing simultaneously different files. And so if your pool have size 1, in this case you do a sequential write, and you can, for example, activate the compression in parallel runs. We had also the time series management, and this version was a reference version for the semi-static experiment. And so the goal with this version was to do all the post-treatment, all semi-static post-treatment in situ, all along the simulation. That means no post-treatment is needed after the simulation, for example, to summarize the data. And now we've just released the new XIS3 version, and we make a pause. We totally rewrite a big part of the internal XIS core engine. That means we touch more than the half part of the code lines, which was a big works. And so the goals for this was firstly to clean code and to rationalize internal concept due to years of eclectic development, to improve the workflow performance and decrease memory footprint, improve the robustness and the reliability of the code, and introducing a new infrastructure of HPC services and model coupling that I will focus more in the next part of the talk. Okay. Yes. Just to improving the robustness and the reliability of the code, we make some many development, more or less outside of the model. The first one was to implement a big suite test for the non-regression to ensure the continuous integration. That means every time you make a commit, the compilation is tested on different computers and different compiler. And also a suite of tests is running automatically, and you can see the results if it is good or not compared to a reference version, and you know if you make some regression or not. Also to help users to debug their workflow, that sometimes the workflow, XIS workflow can be complex. We develop a tools that where we are be able to visualize directly the XIS workflow in terms of graph, and so you can directly see exactly what you do along the simulation. And so these tools can be visualized directly through a web browser. That means directly online. In the same way, we develop visualization tools to track internal memory usage and memory leak, and so you can visualize the timeline and the memory consumption directly through web browsers. We add for debugging more information when in case of XIS is crashing to help to debug, to understand what is wrong, and we add a lot of internal output timer in order to make a better profiling of the performance. So second point is improving the performance and the memory footprint of the workflow. So we make a lot of new development. We develop a new client-server transfer protocol, which is now based on passive one-sided MPI-free communication. We introduce new concept of view and connector for better management of the grid distribution on the workflow. We work on the reduction of the memory footprint by applying new method, new concept, tensorial product properties on the element that's composing a grid. We fully rewrite transformation engine and chaining filter engine. So now we are evaluating the performance, the gain of the performance between the 2 version and the 3 version. Currently, new results. So we take an MO4 configuration at a 25 kilometer resolution with some thousand of process and writing with every 15, yeah.
Okay, you can use the mouse.
You can use the mouse, yeah.
So people online can see it.
Yeah.
We can see it.
Okay, sorry. Every 15 time step. And so this configuration generates about more than 3 terabytes of data in less than one hour. So we compare the reference time with no IO, with iOS, and the time with XIS2 and the time with XIS3. And so for XIS2, you have 13% of overhead, and for XIS3, now there's only 4% of overhead. So the reduction of the XIS overhead has been decreased of a factor of 3. That means directly 8% speed up on this configuration. So of course it will be not the same for every configuration because it's strongly dependent of the IO you put in it. But it's a good, it's a very encouraging result. For the memory footprint reduction, for the same Nemo configuration, it's very memory consuming for XIOS. By comparison, XIS2 versus XIS3, we observe a reduction of 20% of the whole virtual memory consumed on the client plus model. That means a reduction by a factor 3 of the virtual memory that is consumed by just the XIOS client part. On the server part, you can notice a reduction of the virtual memory consumption up to a factor 3. So it's a very encouraging result, both performance and for memory footprint reduction that was attended. So now let's introduce the new infrastructure for services. So what is an XAUSS services? XAUSS services is a parallel and asynchronous task that is running about a fraction of the dedicated pool of server process that is allocated at the beginning of the simulation. So XAUSS is now capable to schedule dynamically the launching of the services in the free resources, and the XAUSS middleware now ensure the interconnection between the model and services and provide mechanism for grid exchange and data flux exchange. And so now this new infrastructure model is so by XAUSS middleware exactly like a services that produce data periodically. So model, service, it's more or less the same for XAUSS. So in fact, by the past, XAUSS2 was providing also I/O services, but it was very hardly coded. That means, for example, for the two level of server, all the clients of a couple model will aggregate data with the same pool of server level 1 that redistribute data on the same pool of server level 2. So we totally change this approach with many more flexibility. Now a model is independent of the other in the workflow and can discuss, for example, for a service reader to read data, discuss for a service gatherer to aggregate data, which itself we discuss with another service writer to write the data on the disk. And so we rationalize totally the way to exchange data flux for the MPI partition. That means you can exchange data between model and services, between services and services, and between model and model. And so now, this way, you can easily enable model coupling. And so we follow the same philosophy that at the beginning of XAUSS, the description of services and model coupling remain very describing in a flexible way through an external XML file. So, how does it work? Imagine you launch your couple model with some resources from different models and free resources for the servers. So you have a big pool of resources. At the initialization, XAUSS is splitting the MPI word communicator, and each model gets its own communicator, and you have a pool of resources, the XAUSS server, that can be assigned later for specific tasks. In this pool of servers, free servers, you can create subpool, which can be, for example, dedicated to a specific model. Look, in this case, with this syntax, we create a pool dedicated to the atmosphere of a global fraction of the resource allocated for the server. That means 1/4 of the resource for the server will be allocated for the pool atm. And for the ocean, we use a fixed number. Maybe 25 servers are allocated for this pool. You have also other possibility to select the resource with the remaining fraction. That's the fraction remaining free servers, or the remaining totally fraction that's in all the free resource for the last pool. So, in the unallocated resources, we are creating a default pool that can be used, for example, for retrocompatibility. It will automatically be selected for models that do not desire to select a specific services. I will explain later. So in this pool, you have the possibility to create services. So, for example, using this syntax, you will create the gatherer services in the pool at pool, as you can see, on a global fraction of the resources. In this example, we create a writer that is named writer1 on the remaining fraction, half of the remaining fraction. We create a second writer, writer2, on 6 procs, and on the remaining server, in the pool, we create a service reader. On the pool ocean, I will create a writer and 30 procs, and on the same resources, we create a reader, and so the service has totally overlapping, and if you want, you can overlap many more services if necessary. On the unallocated servers, there is some default services that are launching. For example, on the default pool, you will automatically a default writer that will launch and a default reader on the same resource to ensure retrocompatibility for XIS2 or define some default behavior for context that do not decide to use specifically services. Sorry?
2 minutes en principe.
Non.
Et?
C'est pas vrai. Oui? Okay. Okay. How do you associate your service? It's maybe pretty simple. That means you can associate service at the context level with for default behavior or at file level. So in this example, I assign the default pool at context level, and for example, for the first file to be output, desire to use a two-level server, and so you can assign the gatherer and the writer, and so the data will be sent firstly to the pool gatherer that will redistribute the data directly to the writer 1 services. In the second example, you send directly your data to the writer 2 services, and the third file is a file in the reading file, and so you receive your data directly from the reader services that is specified. If you don't specify any services, by default, you retrieve the XIS2 behavior. That means you will send, in this case, you will send your data in the default pool and default writer services, and receive your data from the default reader services that live in the default pool. Okay. Sorry. So we have a new middleware infrastructure to manage IO services. For now, only gather, writer, and services are currently implemented. The main interest of this for now is just performance tuning. You can aggregate more parallelism with the services that we can place everywhere, but the potentiality of this new infrastructure will be fully exploited with future development for new services, which can be interconnected with the IO services. That means we are planning to develop offload services, to offload directly a piece of XIS workload that is costly or dedicated resource. Ensemble services to manage efficiently large ensemble run. AI services to make deep learning and inference in situ. And also we want to give them to the user to define themselves their own services, for example, in Python. Okay. Quickly, now it is important in a coupling model to talk about new coupling functionality. Sorry. So now I tell that you can exchange data between two contexts running on two different models. So how does it working? You suppose that you are using XIOS and field and associate gate are defined in the XIOS context file. And so how to decide to send a field to another context. So we introduce a new element, Cooper route, to say, I want to send a field to another context. The context is identified by the model ID, destination model ID, and destination context ID. Very simple, and your file is embedded inside. To receive a field in the XML, you describe from which context you receive your field, with the same idea for the source model ID and source context ID to define. And so, model is. So, what XLS do at context initialization after closing context definition? The grids are sent from source context to destination context and redistributed. And so, you are now able to receive a field on the source grid. And so, you can use a remapping workflow to make the remapping, for example, horizontal and vertical mapping. And in the time loop, from model, you keep exactly the same interface. XOS send field, send your field, XOS receive, to receive your field.
Faudrait que tu conclues.
Ouais. I just a little bit example in the XML syntax, just to see to show you that it's not very complicated to use. So I want to export a field at, that is an alias of a 3D field that live on a 3D grid that is composed of a domain on axis. So it's a source model and the source context. And so you want to be coupled with the destination context, the ocean model. And so you use coupler-in definition in which you make the correspondence between the ID of the field from the source context to the destination context. The ID must be the same. And after that, you are now able to receive this field on the atmospheric grid because the grid has been transferred. But what is interesting you is to get the field on the ocean grid. So you need to use interpolation feature by defining your grid, ocean, and say, I want to interpolate from another grid. So in this case, we select interpolation number 2, interpolation of the axis, and now you can directly receive your field by calling ENES-RI field with a filtered oscillator that is on the ocean grid. And so, with this, you have the scalar for flow. You send your field from your model source, asynchronously transfer. You make the horizontal interpolation on the destination context, the vertical interpolation, and so you can get your field with your model inside your model with ENES-RI field.
Okay, you have to wrap up. Yeah.
Very simple. Finished.
Good.
Okay. So, of course, it's a very simple example, one-way coupling, but you can achieve very more complex configuration by combining more of the ENES-RI for flow. That way you can do two-way coupling, you can couple different time sets, you can mention average accumulated fields, etc., etc. So, it's okay, you have the functionality, some work is some meaning to do to have a stable and efficient couple. That is, we needed, for example, to couple for previous time set, not very difficult. You need to manage the restartability of the coupler, probably implement more interpolation method, and to be sure that your model is very stable, and the worst enemy is the deadlock, and so go to the deadlock entity. So my vision of future is a multitude of model components and services that are fully interconnected for a single middleware, as you can see, with a very simple minimalist Fortran interface, flexible management, asynchronous data exchange for the MPI partition to exhibit more parallelism and concurrency, and lightweight coupling with services or small models that are written in Python or in Fortran. Conclusion, future plan. Of course, we need to stabilize and consolidate the services and coupling functionalities, and we will test the ICON-ESM model. We plan to develop new kind of services, develop a Python interface, totally revisit the ENES timeline management by adding time interpolation, to be able to manage attacking time step, and make ENES restartable. And of course, the main priority for the next years will be the GPU porting on accelerator. That will be, we hope, be easier by the new coding, because now most of the CPU consumption is very localized, is small part of code in the connector and the filters, and we can use an incremental approach, filter after porting filter after filters, to achieve the total porting. So we have not decided which technique to use, language-based directive like OpenSC, OpenMP, modern language like Cocos, because ENES is written in C++, so it will not be very difficult to integrate some feature of Cocos or other language. Thank you.
Moritz is developing Yak, which is yet another coupler. I like the name in the KRZ, and he's going to present the last development.
Yeah, and give a little bit update on the high resolution ICON Earth system model. Yeah, just a short overview. So originally I worked on Oasis 4, but after that was dropped, Oasis went back to Oasis 3 and integrated MCT. And we at DKRZ and the Max Planck Institute started developing something new, because at that point in time there was nothing that was usable for us in parallel. and that's when 2014 we finished the first working version of YAC1. It's included parallel online weight generation and could do everything that was needed for the ICON-ESM system model, but it is independently developed of ICON, so it is a general coupler. In 2020, we finished version 2. It had a significant internal rewrite, and recently we added a Python interface to this version. And currently we're working on a third version of YAC that is supposed to be finished in the next few months, and it allows the dynamic online configuration of the coupling, and we replaced the XML with a much simpler file format. Currently, YAC runs successfully on the various computing systems available in Europe and on Linux and Mac OS systems with little to no porting effort. What does the internal rewrite mean? So in YAC1, I implemented a very complex communication scheme that was hard to debug and maintain. I replaced that, and in addition, I significantly improved the load balancing, because now with YAC2, or then with YAC2, weights were generated in parallel, equally distributed among all source and target processes, which allowed for a very efficient way and very good scaling. Recently, we had a new colleague that added a Python interface because he wanted to do some visualization, and that was much easier for him with Python, and that worked quite well. In addition, we added a couple of interpolation capabilities and the support for multiple YAC instances in a single run, meaning you can initialize YAC at any point for any communicator, and that instance then runs independently of all other instances that are already existing or not. Here's a little Python example that is the whole code that you need for that runs perfectly fine. It starts by registering itself in YAC, generating a regular local grid, defining a field called TAS, starting the weight generation and the setup of the internal data structures, and then it receives this data and plots or analyzes the data until no further data is provided. This little toy can be added to a already existing coupling model, and to specify what other model provides this field, you have to write a YAML configuration file, or currently an XML configuration file, and specify the component that provides this field and specify the interpolation. The interpolation capabilities that were new in YAC2 since the last presentation on the last coupling workshop. I added a new weighting option for the average interpolation, or bilinear, using barycentric coordinate based method, and that looks really promising. I think it's much better than the often used distance weighting. In addition, we improved support for concave cells for the conservative interpolation, and we added 2 new options to the source point mapping, or called nearest destination to source in ESMF, where you map all source points to the closest target points, usually used for river runoff or discharge, for example. The new options are the spread distance, meaning that usually with this method you map a source point to a single target point, but with the spread distance, the data is then distributed to this target point and the surrounding target points within a certain distance. This gets interesting, for example, in the Amazon Delta, where ICON had some issues where too much runoff or discharge was placed into a single ocean cell, which caused problems, and with this distribution, that problem went away. In addition, I added the max search distance, meaning that target cells are only allowed to be within a certain distance. More on that later. And then at the last workshop, Bob Oehmke presented or introduced me to the creep film method, which I thought was very interesting. So I added that as well, including the option to specify the creep iterations. Interesting interpolation method. And then we added a user callback method, where the user provides a callback method, which is called by Yak when it wants to have the weights for a specific target point. And then the user computes these weights and passes them back to Yak, which then uses them for the matrix vector multiplication for the interpolation. And a nice feature of that is that it supports arbitrary combinations of cell, vertex, or edge-based source fields. And at WD, a user uses it to interpolate finite element basis functions directly onto any arbitrary output grid. But it can be used for anything else as well. With Yak 3, we introduced a dynamic online configuration of coupling, meaning a component can query at runtime Yak and ask what the other components defined, which fields other components defined, and then tell Yak that it wants specific fields to get at each time step. This is, for example, interesting if you have an output component, and the output component can then ask at runtime, is the respective field actually available, and then can specify, I want this field at that frequency with this interpolation. In addition, we replaced the XML with a YAML file, with the XML configuration file with a YAML file, because the format itself is much simpler, and we reduced a lot of information from that, which made it much smaller, because we had some complaints that the XML was too big and too hard to read. Here's a little example. These are two configuration files for the same setup, and on the right hand side you have the Yak version in XML, and on the right hand side the Yak 3 version in YAML, and I think it speaks for itself. Oh yeah, and at the last workshop, Bob introduced me to the destination status field, which he, for example, used for debugging of interpolations. I thought that was interesting, and so I wanted to present one method I usually use to interpret the weights generated by the coupler. If I'm not sure whether, for example, the source to target mapping works correctly, I can write a weight file, and then Yak contains a tool that converts this weight file into a BTK file, which can be visualized in ParaView, for example. But another user used a Python script to do something very similar. And this is an example where you have a high-resolution ocean grid, atmosphere grid, where you only see the coast points in red, and then you have a coarser resolution ocean grid in blue. And in this case, I wanted to interpolate the coast cells to their closest ocean cells. And I used the source to target map. However, as you can see, the Caspian Sea is not represented in the ocean and is mapped to some cells that don't make sense in that case. And by visualizing this, you directly see this and can adjust accordingly. In this case, I used the max search distance option and set it to 2.25 degrees, which is around 250 kilometers. So the Caspian Sea is not mapped to anything, and the user has to take care of it itself somehow. In addition, you might want to use the distribution option, and then it might look like this. Oh yeah, I should mention that black lines represent weights going from source to target. Should have mentioned that earlier. Anyway, in this case I use a spread distance of 0.41, which is around 45 kilometers. And since this visualization is in PowerView, you can zoom in on anything and see in more detail what is happening and what is mapped to where. Yeah, so this is one method I use usually. Regarding performance, recently at DKZ we got a new system from Atos called Levanto that is quite similar to the one at ECMWF, and I was asked to present some performance results for the high resolution. No, that is not for the icon, that is just high resolution stuff. There I used, on the system, I used 128 processes per node. I had 2 toy models equally distributed among the nodes. One toy model used a cubed sphere with around 200 million cells, and the other used an icosahedral grid with around 300 million cells. I configured YAC to generate conservative first order weights for both directions. The initialization time shown on the next slide includes the overall setup of the internal data structures. That includes redistribution and computation of the weights themselves. And the exchange time includes a exchange in both directions, and that includes the moving of data and the application of the weights. On the left hand side you have initialization in seconds, and on the right hand side in milliseconds. And for me the scaling looks quite fine. Initialization time for this quite high resolution setup is well within expectable, or well within good time, I think. So usually a setup running for a couple of hours would have no problem spending a couple of seconds at the start for the weight generation. And exchange time scales even better than the initialization time, and with a couple of milliseconds that doesn't really matter anyway. As mentioned before, we have a new colleague at DKZ that is working on visualization. He wrote a tool called Yavis that interfaces with YAC and receives data from the icon, or from the icon atmosphere, ocean, or whatever other model is coupled using YAC. And using the Catalyst library, it can provide the data that it received from the component models to ParaView, which then can generate visualizations at runtime without the need for writing out data to disk and then reading it in again for the visualization. In addition, he added the Python interface, which he used to generate small toys or prototypes for components that receive data from the setup, and then he used it to do output or to plot it. And since Python has a wide variety of different libraries, that makes working with that data much easier. That is a really nice thing for prototyping or for investigating what the model is doing at runtime. YAC 2 is currently in the official release of ICON, and recently I added new capabilities for communicator generation at the startup. And since ICON is not actually MPMD but SPMD, it had some issues with communicator generation and with external models. But in the current release that is no issue anymore, so you can easily add hydrology, other atmosphere, ocean, IO, or visualization. There are various high resolution configurations at the time. On the right hand side you see for the icon grid names the respective grid spacing, and a typical setup is, however, with matching grids at ocean and atmosphere side. This is rather uninteresting for the coupler, but there's also an R2B9 atmosphere coupled with an ocean, also an R2B9, but with a zoomed region where it's interesting, which makes it a R2B10 equivalent. And there's also a setup using an R2B5 NWP atmosphere coupled to a R2B6 ocean, and there are more to come in the future. I asked for some performance results, and for the aforementioned R2B9 setup, I got some numbers. that were generated by a run at our local system using 400 nodes. The atmosphere ran using a uniform global grid with a 5 kilometer spacing and a 30-second time step. And the ocean used this RTB9 grid with assumed regions and also with a 30-second time step. Coupling interval was 12 minutes. The interpolations used were a first order conservative with a 4 nearest neighbor backup and the hybrid cubic spherical Bernstein-Busy patch interpolation. Cool, I did it. With 4 nearest neighbor backup. This method is a higher order method similar to B-cubic or the patch recovery interpolation. The total runtime of the model was 6 hours and it simulated 10 days. And the time spent in YAC for the initialization, which includes weight generation and setup of internal data structures, was at the atmosphere 20 seconds and 60 seconds at the ocean. But actually the initialization of YAC is collective for all processes, and meaning that 40 seconds of these 60 seconds in the ocean is actually the ocean waiting for the atmosphere starting the initialization. So it's 20 seconds on both sides. And the sum of all exchanges took around 60 seconds, excluding the first exchange because that again contains a lot of imbalances. On the bottom you have a couple of papers describing the setup. And nice picture at the end. At the left hand side you have the blue marble photo taken from Apollo in 1972. And on the right hand side, with the help of NVIDIA, some simulation results using ICON, and I think they got it quite good. That's it. Thank you for listening.
Hi, my name is Carolina Arnold. I'm a data scientist at the German Climate Computing Center, and we are working on integrating machine learning applications in Earth system models. Initially, we thought we would like to develop a software toolkit to do that. Now it looks like we are more using existing software because there's a lot around already, so we are more an application of having software. So typical scenarios where people would like to apply machine learning inside of an Earth system model include any kind of subgrid process that is currently described by parameterizations or that is currently neglected due to computational effort. Our collaborators are working especially on cloud microphysics and atmospheric chemistry, but you could extend this to any other kind of subgrid process. You have the possibility with a machine learning algorithm to emulate the subgrid process, and the hope that people have is that you can provide more accurate process descriptions and take advantage of the fact that you have data available, you can do high resolution simulations and so on. So I'm going to give you a one-slide overview of machine learning. This will be very brief. In general, machine learning algorithms are statistical algorithms that learn from data. So you present the algorithm with training data, and then later it is able to reproduce something that is similar to what it has seen during training. Most relevant are so-called neural networks that you can see here on the right side that transform inputs to output layers by going through a series of so-called neurons. These are the individual circles here. Okay, and each of these so-called neurons contains parameters that can be learned during training. So when we say that we train a model, we select a metric, for example, the accuracy, mean squared error, or any other kind of metric that is suitable for your problem. And then we adjust the model parameters to best fit the training set and save the model for later use. And the bulk of computational effort in machine learning is in training the model. So once we have a trained model, we can just use it on any architecture, even on your smartphone. Machine learning models are running easily. So the machine learning scheme that our collaborators would like to use inside of the cloud microphysics module in ICON-NWP is the so-called super droplet scheme. Currently, the conversion of cloud to rain droplets inside of ICON-NWP is done by so-called two-moment scheme. And the updates are done by a bulk moment scheme that is a very crude approximation of what is happening inside of a cloud. Our collaborators have obtained training data that simulate actual super droplets inside of a cloud. So think of a big box of particles, rain and cloud particles, that provides a more accurate, physically more accurate description of what is actually happening inside of a cloud. They then train a machine learning model that can emulate the super droplet scheme later in ICON. And for compatibility with ICON, the machine learning model receives and returns the 2 moments that the ICON NWP expects. So, of course, since it's a statistical algorithm, you should somehow make sure that you evaluate your machine learning model in a really good and reliable way. So the way that people typically do that is that they generate a test set that is not connected to your training set. You calculate metrics on the test set, you go ahead and publish that. So when you search the archive, there's millions of papers by now where people have trained machine learning models to replace subgrid processes in climate models, but they never managed to go back to the original Earth system model and use their model actually within the bigger Earth system model. So in reality, your machine learning model will be applied inside of the Earth system model time loop. It will encounter conditions that it has not seen during training, and it will interact with the Earth system model in any kind of nonlinear way. So this graphic to depict this. So on the left-hand side, you have, in this case, ICON, and on the right-hand side is brain as the neural network. And what people have seen in the past is that the good so-called offline performance, where you work on this test set to the left, this really does not imply that you have good online performance. So you could spend, let's say, 1 year developing a really nice model, only to spend 1 more year plugging it back into the Earth system model and then find out, oops, it causes instabilities. And we would like to shorten this time by implementing a so-called bridge that enables people to quickly use their machine learning models inside of ICON. So we call that quick and flexible online tests. And we have a series of requirements for these tests. First requirement is that we need something that is flexible, because the machine learning people, they like to have very iterative processes of development. So they like to generate new models on a daily basis and try a lot of different things. So we would especially like to avoid hard coding neural networks in Fortran, because that simply takes too much time. We're also looking for a solution that is friendly to machine learning developers. So as few as possible changes to the Earth system model code, just because there are few people who can do both machine learning engineering and Fortran. It should be performant, of course. So we should still be able to run our experiments. We do not expect to run this bridge in a high resolution run at the moment, but you should be able to do small experiments without waiting forever. And if possible, we should use hardware that is specialized for machine learning, so GPUs. This is the ICON program flow where we are coming in now with our neural network. So we are stepping through the ICON time loop inside of the parameterizations, and deep within the cloud microphysics, there are 3 lines of Fortran code that we are replacing with the neural network. So we are replacing just the warm rain processes. We need to call this for every grid cell and every vertical level of the atmosphere. So we are not dealing with a situation where we couple atmosphere and ocean at the surface where the 2 touch, but we really need to exchange the full atmosphere. And at each point in time, we need to send 2 moments for the cloud and the rain out, and we need to receive 2 moments back. So we are sending 4 numbers per grid cell and vertical level back and forth at every time step. So the first thing that we tried out is not using a coupler. It's a so-called embedded Python. So it's a little extension of ICON, if you would like to put it like this. We're using the C4N function interface, which is a tool with which you can use to compile Python code to a dynamic library. This library is linked to ICON at compile time, and at runtime, a Python interpreter is initialized and it executes the code locally. So this is how we visualize this. You have the ICON-ESM running on potentially many different nodes. And then co-located with that, this Python code is executed. So by this, the data transfer is actually efficient because you transmit only a memory address. And then on the Python side, you can read from the buffer directly and write to the buffer directly. But there's a lot of headache associated with this. The major headache is that Fortran is a column major layout and Python row major layout. So when you start reading arrays from buffer on the Python side, you need to make sure that you do not mix up the dimensions and so on. And all in all, this requires a lot of development. So we also decided to use existing solutions to couple arbitrary Python processes to ICON using the very nice Python bindings that Moritz just introduced. So as Moritz just said, ICON now has the possibility to attach any external program because this MPI communicator splitting is working better now than before. And we're using the Python bindings to exchange fields between ICON and Python. Should point out that we have no interpolation at all, so all the nice routines that were developed to interpolate in YAC, we simply cannot use them because we are interested on each grid cell individually. And we need, because of the current setup of the cloud microphysics routine, we need to define one exchange field for each of the vertical levels. Our atmosphere in our little demo case has only, so it has 70 vertical levels, but that's still as you've seen in these talks. So looking forward to YAC 3, I guess. Yes, we implemented this in a demo case for a very simple scenario that I'm going to show on the next slide. So this is the test scenario that our collaborators would like to use, so-called warm bubble scenario. It's working on a torus grid, you see to the upper right. The torus grid is quite small. It has only 20 by 44 cells and 70 vertical levels. The torus is illuminated from all sides, so we call it internally the donut in the oven experiment because it's like a little donut that is illuminated inside of an oven. And it allows the researchers to focus on the formation of exactly one cloud. So this is what you see here in the GIF. It's a warm bubble that is rising. When it starts to cool, it starts to rain. And this is really a good method to study only the warm rain processes, and ice formation is prohibited and so on. And it requires only 2 hours of simulation time. So in Fortran, it runs in about 30 seconds, which makes it really great to experiment with. We were able to integrate both the embedded Python bridge and the YAC bridge to show that it's actually possible to do machine learning inference from within ICON. So this is just a demo plot using the machine learning model developed by our collaborators at Herion that shows that it rains as well in the when you start using a neural network. So when you look at the rightmost plot here, the blue line is the integrated rain in Fortran. Red line is the integrated rain using the machine learning model that was trained on this super droplet scheme. And we are cooperating here with atmospheric scientists from MPI who will tell us if this actually makes sense, because I'm certainly not qualified to offer an opinion on that. We are able to exchange the machine learning model very easily, so you can generate this plot with a new machine learning model in, say, about 15 minutes, which is very convenient for our users. The last thing I'd like to show is the computational performance of the different bridges. So we are seeing here the time that has been spent in the 2-moment scheme using Fortran, which is almost not visible here. It applies the bulk moment scheme. And CFFI, this is embedded Python. And YAC and pipes, they all call the machine learning algorithm through the established bridge. And you see here that currently the embedded Python solution seems to run faster, but I have to say that the YAC bridge is very much under development. I finished this Tuesday morning, so I guess there's still a lot of room for improvement here, and I'll be in touch certainly with the colleagues at DKZ about this. The overhead, so why does it take more time now when we use embedded Python or YAC compared to Fortran? Yeah, of course, we have to now apply the machine learning model, so that in itself takes more time. And we have to somehow transfer the data between the Fortran and the Python processes. So I can give a quick qualitative comparison of the bridges that we have tried so far. And at some point, we will give a recommendation then to our collaborators. In terms of flexibility, so we, using both types of bridges, embedded Python and the YAC coupling, we can do the iterative development of the machine learning model. In terms of developer friendliness, I have to say it's much easier to do this using YAC compared to embedded Python. It's way less headache, at least for me. We'll see how that generalizes to other ML developers. In terms of performance, for the stuff that we need to do, we're kind of satisfied with the embedded Python solution. For YAC, we will see if we can get it a bit faster. And we did not get around yet to using accelerated hardware, but we will do that in the future. One future use case that I would like to highlight here is the possibility to stream training data from machine learning algorithms using YAC. So in this scenario, you would have a weather or climate model running, and at the same time, you would have a machine learning model that is currently being trained. And instead of writing training data to disk and later reloading it again, we would have the possibility using YAC to directly pass the training data from the climate model to the machine learning model, which should reduce the need for expensive data storage. So this is something that we are also going to try out in the next couple of months. This already brings me to my summary. So for better or worse, machine learning models are becoming very popular now for Earth system modeling. And we're interested in providing solutions so that the ML developers can move quickly to so-called online tests. Machine learning model is really running together with the Earth system model instead of tinkering with it offline. And we've demonstrated this now in the warm bubble scenario, that you can integrate the machine learning model using both embedded Python and YAC. And I should also point out that one major challenge here is bridging the communities of machine learning and Earth system modeling, because it's hard to find people who speak, so to say, both languages and who get the mindset of the other community. But I'd like to thank you for your attention and point out the contributions here, especially by Shivani Sharma, who's developing the network. And if climate scientists are looking to get into data science, we are hiring at the moment. Thanks.